All right. I apologize for that. Okay, sorry. Mondays, right? So yesterday I think I mentioned before, I'm a primary chorister, and yesterday in junior primary, I thought it was time to get the wiggles out, and so I suggested do as I'm doing against my better judgment. That's always a bad idea because inevitably some kid chooses jumping jacks or skipping in place, and my lungs, I guess, are still recovering from COVID. Either that or I'm terribly out of shape, probably both, because I was gasping for air at the end, and it took me like a good 5, maybe 10 minutes afterwards to catch my breath. It's tough to sing loudly when you're gasping. So anyway, weird. And today is the day that my son Adam is finally performing as Alexander Hamilton in the schools in his grades or his classes rendition of Hamilton. They're starting at my shot and going to the Battle of Yorktown, and so he's really excited about this. He's been waiting for it for years, so hope it goes well. Right, we were talking about enolate formation. Recall that when we form the enolate under equilibrating conditions, we get the enolate that's more substituted, and then we can alkylate it on the alpha carbon. You can't see the projector, right? Yeah, I do that all the time. What a day. Okay. All right, well, we'll try anyway. We get the more substituted enolate, which we can alkylate on the alpha carbon. The problem, though, that some of you have pointed out is that we only make a very small amount of enolate. And so these conditions are concerning. You've got a nucleophile, ethoxide, which might react with your primary alkyl halide. Now, we're pretending that we live in a world where such complications don't exist. But in reality, if you're going to try to do this, you are going to be worried about what if your thing you're using as your base reacts with the alkyl halide. Presumably, if you put only a small amount of this in at a time, presumably the enolate's more reactive than this ethoxide, so we're going to pretend like it works. But there are some problems, and we'll talk about a workaround for those a little bit later. If, in contrast, you use irreversible enolate formation with this sterically hindered base, you get the less substituted enolate. It's the one that forms fastest, and then you can alkylate on the less substituted alpha carbon using an alkyl halide, and this is just an SN2 reaction. Your text mentions that in practice this only works well for primary alkyl halides or perhaps methyl halides, not for secondary because you start to get some competing elimination products. First, for secondary alkyl halides, the SN2 slows down, and then the enolate can also be a base, and so you start to worry about elimination products. But we're going to pretend that both of these methods work equally well for primary alkyl halides. It starts to get difficult to alkylate, to put more than one alkyl group on a carbonyl compound. So suppose that I wanted to use sodium ethoxide and then just some methyl halide to get this ketone, where I modify one of my two alpha carbons, and it doesn't matter which because they're equivalent. But suppose I want to make this product where I have two methyl groups on the alpha carbon. We might call that alpha-alpha di-substituted because there are two alkyl groups on the alpha carbon. If I were to try to use reversible enolate formation. Presumably there would be some selectivity for this enolate. And so in general, I'm going to allow you to use these conditions to make that product. But your text points out that sometimes the selectivity between these two enolates is not very great. And so sometimes in practice you get a fair amount of the undesired product. When you want to install one alkyl group, sometimes it works fine. When you try to do more than one via this direct enolate alkylation, sometimes you get a lot of the competing product. So your text introduces a couple of workarounds, and I find that this is a little bit tricky, and sometimes students struggle with why on earth we're doing this anyway. We're doing it just to, we're going to show these next two reactions as a way of helping you see a workaround that helps us get to desired products, but then also to introduce a concept called decarboxylation, which has important roles in biology. So remember this is our target compound, all right? So there's a better way to do this, or rather a way that leads to fewer byproducts, though it's going to look like you're taking a step backwards, and that is to start with this beta keto ester. This is called an aceto-acetate ester. And because of this, your text calls this reaction the aceto-acetic ester synthesis, which makes it sound like you're actually making the aceto-acetic ester, but you're not. You're using it as the starting material. So I think that's a dumb thing to call it, but there you are. So when you read in your text about the aceto-acetic ester synthesis, that means this starting material. Okay, so right away we know that because of this starting material, because that proton is alpha to 2 carbonyls, it's got a pKa of around 13, which means right away we're no longer worried about having an excess at any one point of ethoxide that could potentially react with our alkyl halide, because sodium ethoxide is a good enough base to quantitatively, that is 100% yield, give us the indicated enolate. And that is because, of course, the pKa of ethanol is so much higher than the pKa of the beta keto ester. So once you've got this in place, oh, you know what? I got to switch that. Once you've got this in place, now in a second step, you can add your alkyl halide. And the nice thing about this synthesis is, recall that the difficult step up here was the selectivity between this primary and this secondary carbon. But there's no such issue here because the proton that's alpha to both carbonyls is simply the most acidic one and the one that's going to be removed fastest. This proton is way less acidic, pKa of around 20. This one has a pKa of around 15. So I can easily install a second alkyl group with a second equivalent of base. I'm going to generate that second enolate. And again, this is the real strength of this method in the sense that the selectivity for the enolate that you want is totally taken care of by the fact that you've got 2 adjacent carbonyl groups. And then I can install my second alkyl group via an SN2 reaction, and that will give me this material, which I now have 2 alkyl groups on my alpha carbon. I'm going to zoom out a little bit so we can see what we've done. Starting with the beta keto ester, totally deprotonate, alkylate, then totally deprotonate again, then alkylate again. Okay? And there's no selectivity issue because the acidity of that proton between the two carbonyls is such that that's the one that gets removed, and it gets removed at 100%. All right, well, but remember that the thing that we wanted does not have an ester on it, right? The thing that we wanted was this ketone with two methyl groups on one of the alpha carbons. So I wouldn't be showing you this method if there weren't a way to get there. And this is the part that'll be new. But before we do that, any questions on what we've done? Okay, hopefully when I say beta keto ester, your brain is already thinking carbonyl on the carbon that's beta to the other carbonyl or something like that, right? Carbonyl, carbon, alpha, and beta. Other questions? Yeah?
Why can't that be reversed? Why can't it be carbonyl, alpha, beta from left to right?
It could be, yeah. Why couldn't I start counting here? And I don't know why. I think either way, it's a beta keto type carbonyl compound. I tend to think of esters as being higher priority than ketones because that's how the nomenclature rules work, but there's no particular reason why you'd need to call it that way. Other questions? Okay. All right, let's show you how we're going to get from this beta keto ester starting material now that we've doubly alkylated on the alpha carbon, and how we're going to get over here to the desired ketone product. First, we're going to hydrolyze the ester. And that we talked about in the previous section. So we're not going to draw that mechanism. Hydrolyzing the ester would, of course, involve protonating this carbonyl carbon on the ester to turn it into a reactive oxonium ion. Then water could attack directly to give you a tetrahedral intermediate. You'd do proton transfer to trade who's the good leaving group, and you would ultimately kick off ethanol as a leaving group, and that would give you your carboxylic acid. Okay, so ester hydrolysis, I think that's chapter maybe 16, right? So go back and review your notes there if you want to see it. Now, what happens? Well, now anytime you've got a beta keto acid, what I'm going to show you is a possibility. And in practice, we have to add some heat. But when we do that, that converts into our desired product. And actually, CO2. This type of reaction is called a decarboxylation. And we're going to see them a lot in biology and in metabolism. But we kind of want to know what on earth is going on here. It looks like we've basically lost CO2, and then we have to have another proton on that alpha carbon. So what happens? Well, to see this, you sort of have to think about the fact that this beta keto acid can have a self-hydrogen bound structure. You see that if we rotate around this carbon-carbon bond, we can bring the acidic OH group of my acid near the beta keto carbonyl oxygen, where there can be a hydrogen bond between a lone pair on that oxygen with the hydrogen of the acid. And it's a lovely six-membered ring. All the bond angles work out really well. And frankly, the fact that you have two methyl groups here creates some strain that even promotes this kind of shape of the molecule. All right, so understand that when you have a beta keto acid, the acid is already hydrogen bonding with the beta carbonyl oxygen. What happens next then is really easy. If you say, all right, let's have, instead of a hydrogen bond, let's have that beta keto carbonyl actually steal the proton from the carboxylic acid, that would give you the negatively charged conjugate base, right? What I'm going to draw, I'm going to do stepwise because I think sometimes it's difficult when you're first seeing this to see all the arrows at once. But there's evidence that all of this happens in a concerted process. So though I'm going to take you through it step by step, we're going to ultimately draw it differently. All right, so if that beta keto carbonyl steals the proton, then I have a carboxylate here. And what we're going to do now is similar to what we did with a tetrahedral intermediate where we kick off a leaving group, only this is going to be our leaving group. And the reason that's our leaving group is because if electrons kick down and kick that leaving group off, what do we have? We have what looks like an enolate, but it's actually a neutral enol. Sorry, I lost a couple of methyl groups there. Thank you, sorry. All right. Sorry about the disjointedness of the recording. So to review what we did, we started with the beta keto ester. We did 2 sequential rounds of alkylation to install our 2 methyl groups. And in practice, I don't know, I think you can probably do this all in the same pot. That gave us our dialkylated species, and then we used H3O plus, water, and heat. This does ester hydrolysis, decarboxylation, and tautomerization, finally to give us the methyl ketone product. All right. Yes?
So in this reaction, could you use a base instead of an acid for the hydrolysis?
Could you use a base instead of an acid for the hydrolysis? Sure. And frankly, the decarboxylation should work okay in base. Your leaving group there would be an enolate, and that maybe is an okay thing. I think it probably works faster in acid. Yeah. So let's try to think backwards. Let's start with a product that looks like this. And as soon as I draw a ring of any kind, there's a part of your brain that starts panicking. I don't know if any of you have watched the old SpongeBob SquarePants, but there's this, and don't, it's not worth it, but there's this scene where somebody asks SpongeBob a question and then it shows his brain and there's lots of little SpongeBobs running around looking through filing cabinets and suddenly everything's on fire and they're panicking. This is what happens on an exam when you see a ring, but don't, okay? Because the first thing you're going to do when looking about how to synthesize this is notice methyl ketone, and then the second thing you're going to notice is 2 alkyl groups on the alpha carbon. It's an alpha-alpha disubstituted methyl ketone. Okay, if I recognize that and I remember that I use aceto-acetic ester to get a methyl ketone, then I can start thinking backwards sort of stepwise, right? And one of the things I can do is think, okay, what would this look like prior to ester hydrolysis and decarboxylation? Well, the one alpha proton that's left is going to be gone, and what would have been there is my ester. Okay, do you see that jump? In fact, I mean, for heaven's sake, folks, it's just the same problem, right? Only the two alkyl groups happen to be attached to each other. And another hint, if you want to forget about the ring and make these two R groups, you can. That can sometimes make your life a little bit easier. Do you see how we got from here to here by thinking backwards? What would have been at this alpha carbon prior to ester hydrolysis and decarboxylation? And can you make the connection now thinking forwards? If we had this beta keto ester and we use acid and heat, we're going to hydrolyze the ester and decarboxylate. Okay, questions about that connection and how you see it? Alpha-alpha disubstituted methyl ketone. That's the pattern you're sort of looking for, pattern recognition. Okay, and then, okay, suppose I tell you your starting material has to be this and any other alkyl halide. The question is now, how am I going to make those two bonds? Any ideas what starting material I should use and how many carbons it should have? Yes, go ahead.
It's like a dibromo with 4 carbons on it.
You want a dibromo 4 carbons, so something like 1, 2, 3, 4, that. Okay, yes, that looks good. Now, how would this work? Well, going forward, we would remove one of the protons with our base, which is sodium ethoxide, and that would give us the corresponding enolate. Once you got a plan, then to check the plan, if you want, you can draw the forward mechanism, or you can just think through it and just draw the products, confirming that your synthesis is reasonable. So that's going to make our first carbon-carbon bond, 1, 2, 3, 4, and here's the bromo group. Now I'm going to do the second thing as well. The second step as well will be to remove this proton, give ourselves the enolate. And now this is not only an SN2 reaction, that's a crazy looking arrow. Not only is it, that's worse. Not only is it an SN2 reaction, but it's an intramolecular SN2 reaction, so it's fast. Okay. So, yay, this is one of our first reactions for making a ring and making carbon-carbon bonds. Don't let yourself be fooled or tricked or distracted by the ring. Pay no attention to the ring. It's just an alpha-alpha disubstituted methyl ketone, and the only time you need to worry about the ring is when you're deciding what the alkyl halide was. Okay, questions about that? Yeah?
Do we have to use like a specific base to take off the second hydrogen?
Do you have to use a specific base to take off the second hydrogen? Yes. So if our synthesis were in the forward direction, well, I suppose not, but the base we're going to use, oh, I forgot, this is a useful point. Thank you for reminding me. The base we're going to use is sodium ethoxide. The reason we're going to use that is any base that we use has the chance to also attack this carbonyl carbon. And if it does, and we choose the base appropriately, that potential side reaction won't matter, because you've got two of the same group there, and it doesn't matter which one gets kicked off, you still have the same starting material. So yes, whatever this ester is, we're going to match our base so that so that if that base attacks the ester carbonyl, we can't tell that it happened. So yeah, that's a good point. So we would add the base, then we would add our alkyl halide, 1, 2, 3, 4 carbons. Then in the third step, we would add our base again, and that would close things up. In the fourth step, we would add acid in water, and we'd turn up the temperature, and that would give us the desired product. So, and the cool thing about this is it's a few very sort of simple steps, but it dramatically remodels the molecule. The only thing from the starting material that stays in the product is that part. And then the part that comes from the alkyl halide are those 4 carbons. Okay, other questions? Yeah?
Why wouldn't the base just attack the alkyl halide that you just put on?
Why wouldn't the base attack the alkyl halide that we just put on? Right, and that's at, let me draw that intermediate product. This is after step 2, where you've made your first carbon-carbon bond, 1, 2, 3, 4. And you're right, at this stage when you add the next equivalent of base, you've got the possibility that this would attack your alkyl halide versus removing the alpha proton. And I think I think you're right to worry about that. In practice, removing the proton is faster than attacking the carbon because protons are smaller than carbon. And so what that means is that we simply remove this alpha proton. That's the fast step. And then, because the negatively charged carbon is in the same molecule as the alkyl halide, then that substitution reaction is fast. Is that good? Okay, yeah.
Kind of a related question is if attacking the carbon is slower, why doesn't it just attack the hydrogen next to the bromine and then turn it into an alkene?
Right, great question. Why doesn't, if attacking a proton is fast, notice that you have, I'm going to do something I hate, which is draw a proton in a funny direction, but you have a proton that's beta to a good leaving group, so why don't you have the competing elimination reaction? And I believe the answer to that is just a question of pKa's. Yes, protons that are beta to leaving group have lower pKa's than your run-of-the-mill sp3 hybridized carbon-hydrogen bonds, but this one is so much more acidic, and that's what really saves you here. This one would have a pKa, I don't know, but I would estimate in the sort of 20 range, but this is 13. So yeah, and if we're careful and we only add one equivalent, we'll only make one enolate. Good. Other questions? Yeah.
So just making sure that I remember from previous lectures, because the pKa is between 20 and 13, those would not leave in pH 7 normal body conditions, right?
So what would not leave?
The protons.
So if the pKa is 13, at pH 7, would just water be enough to remove that proton? No. Of course, you could have a stronger base in an enzyme active site that might do that. And we'll see that nature will do decarboxylations, and nature can make enolates, though catalysis is involved, because that'd be kind of hard to do at pH 7. Okay, what else? Yeah?
What are we doing with the hydronium and water?
Yep, all of this is, so step 4, all of this is 3 things. It's hydrolyze the ester, and that's chapter 16. Second, decarboxylate the beta keto acid, which, see above for the mechanism. And then finally, tautomerize from enol to ketone. Yep. Okay. So we can do this, and your text has a whole other section on another variation of this synthetic approach. You can use a beta diester. Basically, you could use an aldehyde over here, or a ketone, or a diester, and if we apply the same conditions as we did before, let's alkylate with methyl groups to keep things simple. We're going to do those 2 sequential alkylation steps. Oh, sorry. Okay, that's going to sequentially remove the proton that's alpha to both carbonyls. Then that enolate reacts with the alkyl halide in an Sn2 reaction. We install 1 methyl group, do the same thing for the next one. Now we have 2 esters, and when we hydrolyze them, they're both going to become carboxylic acids. Okay? But if we rotate around this carbon-carbon bond, we can get into a conformation in which that carboxylic acid proton is hydrogen bonding with one of the carbonyl oxygen of the other acid, and we can again do a decarboxylation reaction. CO2 is a byproduct, that's why it's called decarboxylation. And then look at the product that we make from that. This is sort of the enol form of an acid. Ignore the OH group and just recognize this as an enol. So if you tautomerize, again, this would involve simply removing a proton from one of those oxygens and then protonating on the alpha carbon. That will get you to a carboxylic acid. And this is an alpha-alpha disubstituted carboxylic acid. Note the analogy to what we did before with the beta ketoester instead of the beta diester. In our product below, this portion ends up here, only the ester's gone, right? And that alpha carbon ends up here. These 2 alkyl groups come from each of those Sn2 reactions. Okay? So if you see a carboxylic acid that is alpha-alpha disubstituted, you should be thinking, okay, I could have made that from the beta diester that I sequentially alkylate on the alpha carbon. Okay? Let's see. Got another minute, so I'm going to set up a... fine. Just go. Have a good day. I'll see you next time.